So we have multi-armed bandit problem in chapter 2 for reinforcement learning. In this chapter, we will talk about the first multi-armed bandit problem, what it is. Then we talk about the exploration and exploitation, what does it mean. Then based on that, we clarified what's the Epsilon-greedy problem, very simple technique to be used. Then we talk about the upper confidence bound or UCB algorithm. Then we talk about the Thompson sampling algorithm, and we will see how we can solve the, for example, multi-armed bandit problem. And here in this chapter, you're going to see the most basic reinforcement learning algorithm and how we can deal with it with different techniques in simplest way. So let's start with exploration and exploitation. I assume all of you already know that. So exploration means that you want to explore something new, try something new. Exploit means that you need to use your memory, your knowledge of previous things that already happened. We have a very nice example for this. So let's say Taiwan is also like restaurants and foods, right? So let's say you're gonna go to restaurant, and now you're hungry and you wanna go to restaurant. You have two options. What are those two options? One is go to restaurant that you already know, you tried and you know that's delicious, and the price is affordable. That's one option. Second option, going some new restaurant, totally new restaurant. So exploitation means going to where you know, based on the options that you know you have, based on the price and how much delicious it is, you choose one. But exploration is to try something new. Very simple. So definition, it is new. Here the new things to try, and here the previous experience of the use. We have some note here that it is critical. Many times we're going to also emphasize on it that sometimes you need to have long-term strategy and do some sacrifices over here. What does it mean? It means that when you're trying something new, you go to the restaurant that is like the food is very bad, awful, and very expensive. You wasted your money, right? But that is sacrifice to find very good restaurants. Let's say you know 5 already, and if you don't explore among other restaurants, maybe there is very good restaurant that is very cheap and very delicious. You're gonna love it. But in order to find that one, you may try 10, 20, 100 times more. And that's the sacrifice you need to do in order to find that restaurant that you want to go, and that's very delicious. And the restaurant that I'm mentioning is the solution for our problems, basically, in reinforcement learning. That we need to, our reinforcement learning algorithm needs to sacrifice, explore, in order to find the solution. Bring it to the memory. Okay, so now we want to talk about the multi-armed bandit problem. In casino, you're facing with multiple machines, and each configured with an unknown probability of which likely to be win or not. You can play in different machines. Then pull the handler or the handle or different names that we have. And per each one of these machines, you may have different probabilities of winning that already defined built-in in the machine. So the developer or producer of the machine written some code that, for example, for this machine, 25% of time, that's too high, but for simplicity, for a simple example, you're gonna win. Here 75, here 30, there 50. But of course, these are very small in real environment. Here just we have some simple examples. Now the question is, what is the best strategy to achieve highest long-term reward? Think about it. You have multiple machines, you are agent, and you're gonna play, and you don't know this. What is your strategy to play? Yeah?
Try each of them a finite amount of times and then pick the one with the best rate. So play each 10 times, calculate the expected value, and then use the one with the highest expected value.
Yeah, that's very nice strategy. Try each one of them 10 times, see which one you want more. Then you can play that one. That's one of the strategies that we can have. But we want to do now, we want to formalize it in form of the reinforcement learning in order to solve it with different solutions, with different techniques. Okay, nice. So if we consider infinity number of trials to understand the concept, why? Because if we say we have finite number of trials, so how many? Your classmate said 10, but I say 1,000. Is it enough? Maybe no, to get the exact probability. For now, for simplicity, we say, okay, let's say we can try forever to see what is the real probability over here to understand it, but later, of course, we will have a finite number of tries. So this is very nice example of demonstrating exploration versus exploitation. Why? Because as your strategy indicated, at the beginning, you wanted to don't care about the, for example, you play, let's say you play first machine and you win. Are you going to continue forever this machine? No, you're going to, for example, as your friend said, 10 times try. It means at the beginning, we can do exploration. But later, you want to collect lots of reward. And based on the probability that you get, then you want to play on the machine that's higher chance to win. So because of that, then second stage is basically exploitation. So we have question now for you guys. This problem is well known as one state problem. Why? Oh, really? I thought you're gonna think a little bit. Okay.
You have just one variable of success, so either you win or you lose. So this is the one state you can have. It's either 0 lose or 1 win.
Close, but not the answer. Yeah?
Your state is you have to pick from one of the machines.
Uh-huh.
So after you take an action, you're back at the start. You have to pick again. So after you pick a machine, it's like you're back in the original state. Pick again.
Yeah, very close. Yeah, kind of I can accept as answer. So your friend means your classmate means kind of. After, so you have current state, you choose one of the, like let's say you choose one of the actions. Then whatever is happening in next state, if we imagine there is next state, so what is the difference between previous and now? Is the reward changing or something is happening? We are exactly at the same scenario. Because there are probabilities we don't know, and we need to again play one of them. Nothing is changing. The reward is not changing during time or during the part that we have. Because of that statement, we have single state problem that the rewards are not affecting the future rewards, and the distributions of the rewards are also stationary because basically we don't have any option. But of course, most of the problems that later on we will face is not like this. Here we just warming up to getting into the real problems of the reinforcement learning to solve them. So the goal is maximizing the accumulated reward during time, of course. And the note that we have, it is the simplest version of the Markov decision process that we will see next chapter. And because the reason is that we will we do not have many states, we just have one state. But in Markov decision problem, we have multiple states basically. What is the most basic approach to do this? So you answered better answer for this question already, but one of the approach can be, okay, playing with one machine for many runs and get reward. Like I guess I'm the guy, okay, I'm saying, I don't care. Randomly choose one, I just play, whatever. That's one approach, but of course that's not good. Second, so this does not guarantee the best long-term reward, of course. Also, based on the limited number of knowledge and resources that we have, we need better approach. And based on that, we want to see how to solve the problem. The definition for the multi-armed bandit is consider a couple of the actions and rewards. So I can do, so we don't have S anymore here for now, for this chapter. So we have action and reward. We do something and get the reward. So we do the action, get the reward, then the K machines, if reward probabilities, each K number of machines that per each one we have probability of getting reward. So we have PK. Then the value of action A is the expected reward. So per each one of the actions I can get the value. What was the value that we defined in previous chapter? Was the expected reward of the action. And here we don't have S. We have directly or a little bit slight differences because we don't have state anymore. But in next problem that we will have, there will be state. That this expected reward represents us finally the probability of the winning per each one of the bandits or machines. At time step t, the reward function looks like this, that RT is equal to reward of the action t based on the probability that that is hidden for us at the beginning. So formally, if we define the goal is the maximizing cumulative reward or maximizing the R from T1 to T and maximize the rewards that we are getting. If we know the optimal action, and best reward, the goal can be minimizing the loss function. What's the loss function? Loss function is here. I mentioned to you, we have objective function, loss function, reward function, and a little bit clarify for you that what are those generally. With loss function that are famous also in neural network, we can show the differences of between the what it's supposed to be and what we are doing now. So the differences of the optimal or the answer and what is the currently. So we can show that we can define it also as regret that we have. If we play something, so let's say we play one machine and let's say how much regret should I feel? That regret can be also called as loss here, that the differences between optimal reward probability P star subtracted by Q of the AT and the value of the taking action that we gain from really what is happening. You play something, you get some value, Q value. Here, Q of the AT here, not, again, we don't have a state for now, we have just action. And the differences between the value, and we want to sum up and call it as expected loss and show it as loss of the our problem. But optimal reward probability can be also represented in this form. P star is the QA star equal to maximum of the all possible probabilities that if we play infinity number, that is going to be very close. Like if you play the machine's infinity number, of course, after billions of times of running, the probability of each machine that wins how many times will be very close to or kind of very accurate to the P star or optimal value, so that we can say the maximum of those can represent the Q A star or the P star reward of the probability. Clear? So as we said, one of the approaches is playing one machine for many runs. This is naive approach because there is no exploration. Second one, exploring randomly. Another approach can be, we can say, okay, instead of playing, just picking one machine and play forever, play randomly each time. Again, this approach is not reliable because that randomness is completely random. And you want to say, okay, every time I play randomly, whatever. Best for luck. Then everything is on luck. Nothing strategy and nothing you learn. But of course, the exploration preferences of the uncertainties, or we can call it as wise exploration, is the objective that we have. We want to implement some techniques or see how we can use some techniques to do this. And today we are going to see some. So first we start with Epsilon-greedy policy. Epsilon-greedy policy is very simple if you know exploration and exploitation. Load exploration exploitation definition, the restaurant that I explained to you, usual place or somewhere new. So Epsilon-greedy algorithm says toss a coin and randomly, if like 50% of the time, so if it's 50-50, that can be different. So if you consider just tossing a coin, that is 50-50. 50% of the time, explore. Explore means do random actions. The other 50%, use your knowledge. This is whole what Epsilon-greedy says. Toss a coin, 50%, 50%. Play random, do some random action, or use your memory. So that if we are going to use the memory, we mean that we're gonna use the best action that we have among the things, and best action comes from where? Come from Q value that we have, or the value for state that we have. So I formalized in some simple definitions here for you guys. Number A says generate a random number between 0 and 1, like you can use rand function in any programming language. Then if the random number that you generated is smaller than epsilon, choose greedy action. We can call it exploration. Exploitation in this case. Otherwise, choose random action as exploration. This technique, although it's similar, very simple, but it's gonna be very useful. We will use it in different algorithms. One of the famous ones is the Q-learning that we're gonna use it. Deep Q-learning, we're gonna use it. We will see, although it's very simple. Now the question is, so before showing that, what is the epsilon? What should be the epsilon over there, the value for epsilon here? What do you think? So I exemplified with tossing a coin, and that was 50-50. But is that 50% good, or 75-25 is good? And how should I define it for this simple algorithm?
Maybe the average of the word that you try 10 times and you say the average of the word. It can be an essence.
Can be, but yeah, not the answer.
You should start by
Exactly.
You start from 1 and you repeat 0.
Exactly. So the answer is, all right, we say we don't know the value. And if I say you 50 is good, you can say no, it's not good. How you say that? And you're right. I cannot tell 50 is good. Can I say 90 10 is good? No, I cannot say. To deal with this problem, we have a technique called epsilon decay. That's what we do. At the beginning, we say, okay, at the beginning, we don't know which restaurant is good, right? Let's say I'm new to Taiwan. I don't know anywhere. This is valid for some of the students that I know. They are very new. I don't know anywhere. I just explore. Then we increase the epsilon value so that we say, okay, everything is random at the beginning. Then gradually, by the time passage, we decrease it. After 6 months, after 1 year in restaurant case, we say, okay, we explored enough and come exploit. Just use your own knowledge. Don't explore too much. This is a very clear example of what's happening with epsilon decay that here I clarified for you. Is it important to know? Of course, it's very important. We're going to use it in even very nice algorithms, very advanced algorithms. Some of them still are using these techniques. It's kind of similar to if you've studied neural network or deep learning, kind of similar to learning rate, but very applicable in reinforcement learning, Q learning, for example, SARSA, eSARSA we're going to study, then later deep Q learning, and so on. Clear? Any question? So we say in multi-armed bandit by Epsilon-greedy policy, action value is estimated by using past experiences so that we can say we can have averaging the rewards of action that we have observed up to current time step. How to represent it? Like this. We can say Q value of the action, Q of the A is equal to, for example, average of the NT is number of times that how many times we played on a specific machine. So then times the reward of the sum of the rewards that played that specific machine. This indicates the Q value per each one of the machines for us. So per each one, we need to calculate different Qs so that we have Qs that indicates what is the average values that we've gotten there. And this one over here that represents if we played that machine or not. Just times the reward. And what's the reward there? If we win or lose. So if we lose, you can say, okay, -1 or 0. If we play machine A we play. If we win, we can say, okay, 100, +100, or +1, whatever the reward it is. Who is going to define it? You guys. How are you going to define it? By knowledge of working with different reinforcement algorithms to know what should be supposed to be good there. But for example, if you have a problem like path planning from here to end, for the end result, we usually give big reward. Unless we have for each step some rewards, then it's still supposed to give big reward for the success too. Like when you were a kid, you were doing something nice, your parents were saying, wow, very nice, give you chocolate or appreciate you, then you were happy. Then you remember that action and you try to do it again, something similar. Now, you may say, okay, we have the Q of A, what to do with it? This Q is just indicating some value. What to do with it? That's very simple. We come to the next step. We get argmax of the Q of the A. That this says argmax says Who knows what? Who doesn't knows what is it? Is there anybody? Argmax. Oh, okay. So argmax says get the maximum and return the index or return the item itself, not the value. So you have multiple values, multiple parameters. Which one is the max gets it and not returns the value that is inside, returns whole of it or index of it. So that here we can get the action, which action is the maximum of the queue, and put it in A star T, that is the optimal policy or optimal action that we have. So any question? So if you run this approach, of course it is going to work, but what are the challenges? Because like you do this in loop, you try, Epsilon-greedy each time, then update the queue and get the best action. And during time that is happening, based on tossing a coin that you have, then sometimes you picking this, you're picking random action, picking random machine, or sometimes picking the best action that is possible and playing. And during time, if you especially apply epsilon decay, it is gonna be work. But what are the challenges that we have in this approach? We say if we can tune epsilon parameter well, it will have good results. But although we introduce the epsilon decay, but how much should be the decay value? How fast? It's still easy to. So it should decay like in 1 million or 100 times or 500 times. If you can do that, that's nice. It works pretty fine. So, but still it is challenge. And you may, okay, now ask, if I'm gonna use it, how gonna find it then? I mean, epsilon decay rate. What's the answer? Any guess? Again, we said the challenge is in epsilon-greedy is defining epsilon, right? The amount, let's say 50-50, picking which action, the amount of value. Then to solve that, I said we can have epsilon decay. At the beginning, very random, then decrease it by the time. After a while, no random anymore, just best actions. Now, the question is the scale. How fast should be this decay happen? How we can find it?
We could just use another epsilon-greedy problem. So we use e to the power of minus ak, and for our a we use an epsilon-greedy problem. Then we'll use the something like 50-50, for example. You know what I mean?
Yeah, I know what you mean. You introducing a smart approach to do that, and yeah, we have those techniques. Yeah, you can have some technique to. Let me explain the simple one first. The simplest one is just try. One time try 1,000, 1 million. One time try 500. One time try 100. Then you will see what's happening. And so when is the waste? It converges kind of. Then it's not finding better values. With trying different values for epsilon, decay value, amount of decrease of the exploration to exploitation, then you will find it out. Or you can write some codes to do that, try different values, as your friend said. Write some equations that tries it and finds what is the best value to this decay value. Are these important that I'm explaining to you? Very, very important. You're gonna code these, you're gonna implement these. If you cannot do these things that I explained to you, you're not gonna be able to simply run Q-learning, for example. one of the most basic algorithms that we're going to use to solve problems. So these are very important. You're going to try it, whatever I'm explaining here yourself. Then, so defining proper value of the epsilon-greedy is challenge, as I said, and the solution, one of the solutions also can be upper confidence band, UCB, that we are going to introduce now an approach that relies on number of times that we apply one of the actions. It is also kind of smart to say, okay, let's say I have 3 machines and I'm exploring. I'm in mode of exploring by even the previous algorithm, epsilon-greedy or whatever it is. I'm exploring. It means that trying randomly, don't care about anything. But after 1,000 times, I just try 10 times of that machine, but a lot of these 2 machines. Is it good? That's not very wise, because that's random may happen, right? Maybe mostly these 2 happens, that one is not happening a lot. So upper confidence band or UCB is going to propose an approach to deal with this problem, and let's see how we can do that. The definition is favor exploration of the actions with strong potential to have optimal value. What is the optimal value? Remember, we defined today, and I said very important, right? I'm going to use it a lot, and I'm going to use it up to end of class. Please again. So when I'm telling optimal value, now you should imagine the equation there. What is the optimal value? So we are going to favor exploration of actions that leads us to have optimal value. Let's have a look. So we want to define a band per each action that band indicates how confident we are about the Q value of that action. And now again, you should quickly imagine what's the Q value and what I'm talking about. Less confidence, band will be big. More confidence, band will be small. And how are we going to define the band? We are going to use this equation, simple equation here. First, have a look at the equation. Next slide, we will see example in visual form and example of the numerical form that you're going to see what's happening. So we want to define the band that band helps us to pick the action among multiple options that we have. So here we have the UTA, so upper bound of A that we want to calculate, upper bound of the action that we want to calculate is equal to the square root of the 2 times logarithm of t, that t is the number of the choosing actions t, over NTA, that NT is number of times that we've chosen one, that is specific machine, the action or the action that we've chosen. Because here the actions are indicating different machines, right? A1, A2, A3, machine A, machine B, machine 3, for example. So calculation of the 2 times logarithm of t, you know, we have, it is increasing exponentially, and getting logarithm decreases the value, 2 times of that over the that per each machine, how many times we played it. This can give us an upper bound of that amount that indicates and will help us to choose the best action. That best action means here that the action that we have more confident on it to be played. So what else we have point here to mention? Also, I say that this NT, number of times that you are playing, if it's larger, give us a small confidence, decreases the confidences. Because we want to give more chances to machine that I explained here, we didn't play too much. Because if we played thousands of times this machine, just 10 times of this machine, we cannot be confident about this machine, right? We want to give more chance to this machine by the confidency that we're going to try. We want to define with that term over there. So the same explanation. In fact, we prefer actions that we haven't had a confident value estimation for it. And UCB algorithm measures the potential of the upper confidence band of the reward value by Q. And so it is selected the greediest action to maximize upper confidence band as follow. And each time, after we calculated the upper band, we add it by the QT of A. And based on this, we get the maximum action that we're going to have it. So the Q of the A, the value of the action that we have for each machine, added by the confidency that gives us the value. Maybe one of the machines Q. So why we are adding this? Because if the machine has very high chance to win, of course we don't care anymore about that machine if he played or not. Right? This machine is 90%, 80% of winning chance. Although we tried it millions of times, we tried it 100, 500 times, we still want to play here more. But sometimes also try it. That's the reason here we have this term, and getting argmax in greedy way. Greedy means we want to always win. We want to get the best one and use it. So let's see example to clarify everything. For UCB, we have an example here. In this example, let's assume the Q values of, we have 3 machines, machine 1, 2, 3. 1, 2, 3. And Q values of the machines initially are 1. What does it mean? It means that the value of playing each one of these are 1 equal. For simplicity, we just get 1. And of course, this is going to be update after playing. And this n indicates the n of A1, indicates how many times we tried it. Here, for example, 200 times we tried machine A, machine B or machine 2, 150, and machine 3, 750. Okay? And we had this term already here, how we can calculate the UT. Now, we want to, using this equation over here, see what is the result and how we can calculate what's going on. We say upper bound of 1,000 of A1 is equal to 2 logarithm of the T. What is the T? We played 1,000 times. Over NTA1. How many times we played that machine? 200 times. Then we calculate the result, we get some value. Clear? We just place the values that we have. Number of times, the number of times that we played machine, and the Q value. The Q value is still same. We are not talking about it. I will visualize it there. Then for second machine, everything is same. For this machine, we played 150 times. Then we get some other value. And for third machine, 750, and we replace and calculate, and we get 0.29. Now, let's visualize it. So I'm saying these are Q values. Q value of A1, A2, A3. Why these points over here? Because they were same, and they are in one horizontal line. The Q values could be different, and these values could be upper and downer, first of all. Be careful about it. Then what we've done, we calculated different upper bounds. And if we visualize it, like the 0.1, 0.51, 64, and 29, we may have something like this. From this point, we go up for 0.51. First case, 0.64, 0.29. And what we're going to do, we're going to choose the one that has maximum value of the upper bound to play. So we can say in machine 2 we have higher hope to play, to win the game and get higher reward. So this is going to change during time. This point is going to go up, down, and this one's based on where the point is, the upper confidence band going to change. And based on that, we're going to try different machines, and this algorithm is going to tell us every time, instead of tossing a coin like Epsilon-greedy and choose random and best action, moving whole procedure much more smarter. So I didn't put the comparison here. If you have a look in the book, there are comparisons between Epsilon-greedy, for example, or UCB on different algorithms. Since you have an assignment for this, you're gonna compare it. You will see yourself that which one is working better in one problem. Okay, any question? Is everything clear? All right, so I'm gonna rest 2-3 minutes, then we continue with Thompson sampling. All right, so now we're gonna discuss about the Thompson sampling algorithm, and let's see what is it doing and what's the differences between previous ones. We say at each state, at each time step, we want to select action according to the probability that it shows that it is optimal, the action that we are doing. We want to talk about mostly probability form of choosing an action in Thompson sampling algorithm. So first of all, before talking about the Thompson sampling algorithm, we need to talk about the beta distribution. If you haven't heard about it yet, we can consider Q of A, which essentially is success of probability theta, that we will see next slide how we can define it as beta distribution. We will see the equation. And here we can have two terms, the alpha and beta, that corresponding to the cons that we have succeeded or failed on the gaining reward from each one of the actions that we are doing and running on the machines that we have. So Thompson sampling actually samples an expected reward Q of A from, so this is expectation we had. And whenever I forget to explain to you, in machine learning, or actually we are in machine learning field of area, whenever you see hat, it is like expected or estimated of the something, estimation of the something. So expected reward of the QA from prior distribution, we will have the beta, or beta distribution of the alpha I and beta I, that we're gonna see in a minute. What does it mean? Then the best action selected among the samples. So beta distribution says we can have an equation like this, that probability of the theta is equal to 1 over beta, alpha, and beta. So this is beta distribution indication, and the alpha and beta are two input arguments over actually times some that comes over, both are same, times x power of the alpha minus 1 times 1 minus x over beta minus 1. And this is the term that clarifies beta distribution for us. What does it mean? It means we want to feed two parameters alpha beta and get the probability of the theta. And this alpha beta is going to indicate us the distribution over a plot. So we will see quickly now that the distribution that we can have, we can move it to the right and left in order to they predict the probability that we have there. So this comes from this beta distribution over here. The alpha theta is the integral of the u over u power to the alpha minus 1 times 1 minus u over beta minus 1 du. That are you going to like? Are we going to prove it and how this is coming? Not really in this course. If you are interested in, just have a look. What does it look like? It looks like this example that I'm going to show you. If you have the input argument alpha and beta as same values and small values, it means that the distribution over the probability of, for example, x here is same. What if I increase it? So if we increase it, it goes to be like not exactly Gaussian, but looking like Gaussian distribution. But here, if I increase it more, but equal, so looks like Gaussian distribution. So these are input arguments that I'm feeding to the equation, alpha, beta, and this gives me the probability distribution that I have here. What if I have like alpha 1, beta increased to 6? Then the curve looking like this. If I have something like alpha 2, beta 2, looking like this. And if I have alpha bigger value than beta, the curve will look like this. What is the intuition here? The intuition is here, okay, get idea, when we are talking about the probability, when we want to talk about the probability of playing machines, can we use this term somehow, this equation, this beta distribution somehow, to play with these parameters to finally find good distribution of which machine to play? The answer is yes. Thompson sampling is trying to do that. So, clear up to here? And if you want to try, I put the link. This is implementation online. You can implement it yourself, the term. I think, I'm not sure, I think I've used also in the code. I should check it. I developed some examples for you. But anyway, if you go to that link, you can try different alpha beta values and see what's happening also yourself. And the idea is somehow using this beta distribution in order to solve our problem, multi-armed bandit. Can we do that? Yes. How? Let's see. The idea is the estimation of alpha beta values by changing them continuously, and it changed the shape of the distribution related to possible actions that we can have. And if we repeat this many times, actually we can call it as sampling the distribution, and getting Q values, we can form the true estimation of the probability of the which machine winning is. So how? Let's visually see how. Let's talk about the Thompson sampling in iteration 1 and assume that the distribution initially is alpha 2, beta 2. And we have 3 bandits, 3 machines. Machine 1, machine 2, machine 3. And these are indicating Q values for us. So now, first of all, we need to sample Q value from each distribution, and that randomness is based on the distribution probability here. So I want to get one random point for each machine. Then based on that distribution, I'm going to play it. So I do it for you. I played like generated random numbers based on this probability distribution, and you can see that, okay, maybe here for machine 1, here for machine 2, and here for machine 3. So is there any reason that this is happening? No, because the probabilities are completely similar and are kind of totally random. Next step, I'm gonna say, okay, the Q value is maximum here because this point shows higher value for me. So this, after taking these numbers, if I take the maximum, the one that shows me the higher chance to win, it is kind of definition of higher chance to win, although it doesn't make sense here for now, but later it's gonna make sense. So that I'm gonna use this point and play this bandit machine. Then after playing it, the idea is updating the alpha beta parameters for the cases of the winning or losing. If I'm gonna win, here I'm gonna add the alpha. And if I'm gonna use, I'm gonna add the beta. Okay? And what is going to happen so far without explanation? Look at here. When I was changing alpha beta, the probability distribution was changing here. And now that idea that I had here, for example, when alpha is greater, so the distribution moves to the right and to the left, and if beta is greater. So that the idea comes from there, from beta distribution, and I'm gonna tune it by winning or losing, being winner or loser. So in this example, iteration 1, I generated for each machine one sample points. Then that one shows higher value, and I played it. Then let's see if we win here. We could have lost. We don't know. We pull lever and we won. Just assumption. Because you're gonna try it, right? In this case, let's say we won. What is happening if we won? We increase the alpha by 1. If we increase the alpha by 1, we have alpha 3, beta 2. And you visually can see that this distribution tends to the right. And when it tends to the right, we have Q here, and it is increasing. And now you can get the key point. If we randomly, based on this distribution, choose random value, it is much likely to be in winner case, to be in right side. Why that happened? Because we won the game. Clear? Okay. Here I'm gonna show iteration 2. Let's try it again. So what we do, generate 3 random numbers based on the distributions that we have. Now in this case, let's say we have this one, and this one looks like the winner. So the Q value is maximum there, and we're gonna play this time bandit number 1. So now let's say if this machine loses, what we do, this time instead of alpha, we increase the beta. If we increase the beta, the curve tends to the left by the beta distribution that the term, that equation that we defined. And now you can see this tends to the left, this tends to the right, and this is like as initial that we had the machines. Now, what if we continue this a lot? Based on the machine chances that winning and losing, we will have distributions like this, for example. That shows bandit 1 has very low probability to win after trying, for example, I don't know, thousands of times. I've showed 200 here, for example. You can sum up all the tries, becomes how many times we tried here. So, as I remember, these are real values. I don't know, I should check it. I think the plots are correct values of the trying. Then it is here. In bandit 2, like 75% of winning chance, for example, and here 25 times of winning chance. And this shows us that, okay, bandit 2 is more likely to win the game and try that bandit with Thompson Sampling algorithm. Clear? Any question? So the same thing that I explained to you. Now we're gonna go see some implementation example that I've done for you for Thompson sampling. And after we discuss it, we have one assignment for you that you're gonna, for next week, compare. I implement the most challenging one. I will also share the code with you. Now I will explain it a little bit. Then you're gonna also implement two techniques that we studied today, Epsilon-greedy and UCB. Then compare those three together. Plot the result to see, okay, for example, 3-armed bandit machine, which one of these techniques working better to collecting reward that we have. And I also noted that you need to plot total reward and 1,000 iterations that, as we are going to see in the example. Okay, this chapter also is finished. Let me conclude, then go to code. We discussed and introduced multi-armed bandit. We saw Epsilon-greedy algorithm that is very useful in future. We will see. We saw UCB and how UCB algorithm can cover the problems of Epsilon-greedy. And later we saw one sample of Thompson sampling and applied it on multi-armed bandit and understand concept how it is working. And that's it for first chapter of the multi-armed bandit based on reinforcement.